Hello, and welcome to the Electric Current and Resistance Unit of PHYS 1201. In this lecture, we're going to develop a model of what is happening in a physical object when there's an electrical current running through it. Most of the things we've studied up to this point have been things that we could directly observe in various ways. Moving objects, you can observe the forces that are exerted by electrical fields, and so on. But now we're talking about electrical current, and you just can't see electrical current, so you need some way of being able to observe it and know that it's there. So it has a lot of effects that make it possible to know when it's occurring and also make it possible to measure it. Some of them that are easy to observe is that it causes things to get warm. When a current flows through a material, it warms that material up. Not often as much as, say, the current flowing in a stove element. Often this is a subtle effect, but it's there. Current can deflect a compass needle. We'll talk about that more in an upcoming unit on magnetic forces and fields. And it can cause some things like light bulbs and the air, when lightning is passing through it, to emit light. Whenever current flows in a material, there have to be some sort of charged particles which are moving inside it. We call these the charge carriers for the material. And of course, in metals, where we know the electrons are mobile, the electrons, unsurprisingly, are the charge carriers. But there are many other possibilities. If you have an ionic solution, such as salt in water, then both the sodium and the chloride ions are charged and can move around, and this movement will result in current. Note that the material remains neutral overall. A current running doesn't cause the material to become charged. The other thing is that even when there's no current running in a material, the charge carriers are always in random motion. They're usually frequently colliding with other things in the material. What actually goes on when a current is flowing may not be what you would have expected. Here we have an example, a metal, and we see that there are the metal ions, the atoms, minus their conduction electrons, and here's just one conduction electron. There would be a whole lot of others, but I'm just showing one. And to make a current flow, we need an E field inside the conductor. Now remember, a conductor in electrostatic equilibrium must have an E field inside it that is zero. But that's because equilibrium means none of the charge is moving around. But now we're talking about a metal that has current in it. So what happens? We create this electric field inside the metal, and that electric field will cause the charge carriers, the electrons in this case, to accelerate. So they're still going to carry out the random motion that they always do. They're going to bounce about, bouncing off other things, but that constant acceleration for an electron in the opposite direction to the electric field, because the electron is negatively charged, is going to cause the charge carriers to gradually drift, so that superimposed on that random motion is a slow drift in some direction. And rather surprisingly, in a metal, the typical drift velocities, or drift speeds we talk about for electrons, are of the order of about 10 to the negative 4 meters per second, even 10 to the negative 5 meters per second. Very, very slow, even though the random motions of the electrons in the metal are actually very fast. It's sort of hard to get your head around the numbers involved in this, so let's think of it scaled up. Let's think about what it would be like if cars on a highway moved the way electrons in a metal do. Well, you would get in your car and you would get on the highway, and your car would be executing random motion. It would be zipping about, colliding with other cars, colliding with these barriers all over the road, and colliding with the edges of the road. And it would be carrying out many, many, many collisions every second. And in between these collisions, it might be going something like 3,000 kilometers per hour. Well, this random motion would be about some average position, and it really wouldn't seem to change. You wouldn't appear to be making much progress. But if you watched for perhaps 10 hours, you would find that you were now executing random motion around some new average position that would have drifted along somewhat. And so here is the distance you've drifted. And with this 3,000 kilometer per hour random motion superimposed on that would be this drift, so that after 10 hours you would have made about 100 meters of progress down the highway. So, first of all, I don't want to encourage anyone to drive this way, but second of all, you have to realize that when we impose an electric field on a metal and cause a current in it, the actual change to the motion of the electrons is minuscule, basically not noticeable. We don't make them go any faster than they would normally, even if we hadn't imposed an electric field. Nevertheless, the electric field inside the conductor does make current flow. It creates this very small drift velocity for the electrons in the metal. The reason a significant amount of charge gets transported is not because the electrons are moving fast, it's because there are so many electrons in motion. And now, if you think about what's going on, let's say you're using a fully charged capacitor to move electrons. So you have this fully charged capacitor and you've connected a wire around from one plate to the other. So electrons are going to leave the negative plate and gradually drift around the wire to the other end. Why is that? Well, we know there's an electric field in between the plates. And anytime there's an electric field, that implies a voltage. Right? So there is a voltage, a difference in potential between the two plates. But remember that potential is a function of position alone. And so since you see a potential rise as you step from this plate over to this plate, if you walked all the way around this way as well, you would also see the same potential rise. And wherever there's a potential rise or drop, there is an E field. So there's an E field in the wires as well. It's much smaller than the E field in the plates, because it's the same delta V over a much larger distance. But that's an E field inside a conductor, and so it causes charges to accelerate. They then carry out all their random collisions, so they don't really gain any speed, but it does make them drift. If you were to remove that E field, say by disconnecting the plates, then the current stops very suddenly because there are all those collisions going on with the atoms in the metal. And so any drift velocity of the electrons dies away very quickly. Part of the reason to know about this microscopic model of what's going on with current is that it helps you avoid a very common and persistent misconception. So, charge flows in a wire or resistor because it falls through a potential difference. And so the electrons which are leaving this plate and arriving at this plate are going up through a potential rise, but that means they're losing potential energy because they have negative charge. So charge is losing potential energy when a current is flowing. That is true. So far, so good. But students often think, as a result, that the charges must be gaining kinetic energy. That can lead to some really wrong thinking about what goes on in circuits. That is totally wrong. As we've seen, the electrons barely move any faster because of the current than they would be normally if there were no electric field. All of that lost electrical potential energy ends up becoming thermal energy in the wire because of the electrons colliding with the atoms in the wire and transferring energy to them. So this lecture is broken into a part 1 and part 2, and as usually happens when I do that, that means I'm going to ask you a question, and you should answer it before you go on to part 2. So as usual, if you're in my course, you'll be answering that question on Moodle. If you're just watching this on YouTube outside of my course, then I'd encourage you to write down your answer and commit to it before you go on to the next lecture. So let's think about current in and out of a light bulb. Here's a wire and a light bulb, and then a wire out the other side of the light bulb, and these wires must be connected somewhere, say to a battery or something that's making current flow. And so I want you to think about the current going through point A and the current going through point B and compare them. Is the current through A bigger than the one through B? Are they the same, or is somehow the current through A smaller than the current through B? So come up with an answer and then go on to the next lecture.